Hello all, I am Praveen. I am here with my colleague Pranav to deliver our Journal Club presentation on research paper Global Pattern of Trends in Stream Flow and Water Availability in Changing Climate. This paper was published in November 2005 in the journal Nature. Motivation behind this work is the assessment of the impact of climate change on water resources. We know that due to global warming, rainfall patterns are changing and increased temperature has resulted into higher evapotranspiration. So to understand the sustainability of water resources, quantification of the same is necessary. Also, the development in the field of climate change research provides new tools with better understanding. For example, Intergovernmental Panel on Climate Change assessment reports provide different scenarios in climate change. Objective of this study is to assess the impact of climate change on global water resources and identify the trends in stream flow and water availability across the globe. Methodology. It consists of four steps. Step 1, selection of the river basins. Step 2, the conversion of basin average model annual runoff to model stream flow. Step 3, selection of climate model based on root mean square error. Step 4, trend analysis of stream flow. These all steps are explained in following slides. Coming to the selection of river basin, from 663 gauge river basins, 165 gauges were selected for the analysis of hydroclimatic change. This selection follows certain criteria. A basin with at least 28 years of data and no more than 10% of values missing during the period of record. To avoid the overweighting of relatively gauge-rich Europe and North America in the analysis, only the basin with drainage area greater than 50,000 square kilometers were included for those continents. Net divergence for irrigation were required to be less than 10% of mean flow. The monthly time series of observed discharge were obtained from Global Runoff Data Center and averaged to annual values for all analysis reported here. The delineation of drainage basin associated with each gauge was determined by use of simulated topological network (STN30P). The conversion of basin average model annual runoff to model stream flow. For year I, the conversion of from basin average model annual runoff Y of I to model stream flow Q of I was given by equation 1. For each model and each gauge, the value of R was assigned to difference between the lag 1 autocorrelation of annual values from observed stream flow and the lag 1 autocorrelation of annual model runoff. The initial value of Q was set equal to time average value of Y. Next. To maximize the signal to noise ratio in this analysis, an ensemble of models is used. The realism of hydroclimatic simulation varies across models, so ensemble is formed from subset of models and selected based on performance. The models were ranked with respect to root mean square error of the logarithm of long-term mean discharge per unit area. The logarithmic transform is commonly used in hydrology because flows can range over orders of magnitude. Out of 21, the 12 models of 20C3M, that is 20th century climatic coupled models experiment are retained with the lowest error for use in the ensemble analysis presented here. Next. The trend analysis of the stream flow is carried out by using equation 2, where D represents the difference between the average annual stream flow for 1971-98 gives sample size M and 1900 to 1970 gives sample size N. S represents the sample standard deviation of pooled annual stream flow time series, and R gives the lag 1 autocorrelation of pooled annual stream flow time series. Next.
Results and discussions. Figure 1 shows the annual runoff rate stream flow per unit basin area in mm per year. Figure A shows the global distribution of the mean values from the stream gauge observations. Here, area of each circle is proportional to runoff and each circle is centroid at the gauged basin centroid. The figure B shows the global distribution of the ensemble geometric means from 35 model runs. Here the red color shows the gauges with the mean values less than half the observation values, and blue color shows the gauges with mean values greater than the double of the observation values. Here the geometric mean was used because runoff estimates varied greatly across the model for the given gauge. Figure C shows the observed versus model ensemble mean. Figure D shows the observed versus model ensemble standard deviations. In relation to the observed values, the ensemble mean was large in some areas like Africa, Northwest North America, and many more, while small in the southern South America and northern low latitudes of America. Despite the presence of these large scale local differences, they have a strong global correlation. Figure 2 shows the global distribution of the trends in the stream flow for the two time periods. The figure A shows the stream gauge observations, and the figure B shows the ensemble arithmetic means of 35 model run Z values. The pattern of the hydroclimatic changes indicated by the ensemble mean of model trends resembles the pattern of the observations. Means the figure B has some resemblance with the figure A. The resemblance can be seen as seen for the red spots as in sub-Saharan Africa, southern Europe, South Australia, while for the blue spots as in the southeastern quadrant of Africa. Despite the presence of similarities, there the differences are there and it is apparent. Northern Eurasia shows highly upward trend for the ensemble model. The difference in the sign is there through the Central America, Northeastern Europe, Central Southeast Asia, and the correlation between the ensemble and the observed trend is plus 0.34. And when I say the difference in the sign is there means there is change in the transition of the spots from the red to blue color or blue to red color from figure A to figure B. And the figure C shows the plot of observation against means of 35 model run Z values, and the linear regression line was drawn using the following formula. The figure 3 and figure 4 shows the relative change in the runoff during the 20th and 21st century time period respectively. The model projection of the 21st century is dependent on the assumption like change in the greenhouse gas emissions, solar activity, volcanic eruptions, etc. Figure 3a shows the ensemble arithmetic mean of relative change in the runoff for the time period 1971 to 98 calculated by the formula as described in description. Figure B shows the number of runs showing the positive change minus the number of runs showing the negative change. Figure 4a shows the ensemble arithmetic mean of the relative change in the runoff for the period 2041 to 60 as calculated by the following formula. Figure B shows the number of pair of runs out of an available total of 24 pairs showing a positive change minus the number of showing a negative change. While comparing the figure 3 and figure 4, almost all the model runs agree on the direction of the 21st century change in certain regions. Like we've compared the figure 3a and figure 4a, there is 10 to 40% of increase by 2050 in the North America and Eurasia, as we can see from the dark blue and purple colors, and the decrease in the southern Europe and southern Africa, etc., as it can be seen by somewhat orange or yellow colors. And on the conclusion, we can say that on the basis of this analysis, significant part of the 20th century hydroclimatic change was externally forced. Hence, large changes can be expected in the coming decades, and that climate models can help now to characterize the future changes. Hence, it is necessary to include the projections of the forced hydroclimatic change as factor in the assessment of water availability, water management, and also in economic and ecological assessment and planning. The reference to this paper is this. Thank you.